on the RLC circuit. Sometimes all three elements or LR or RC or LC. So initially the switch is at position 1. I'll switch on the cell. Let R be the resistance of this. C be the capacitance. Initially, let's assume that no charge in this. So I'll switch on the cell. So now what I'm going to ask is, what about the current in the circuit? What about the charge in capacitor? How do it will vary? So we took it for granted, like in all capacitor circuit, no? The moment we switched on cell, we assume that the capacitor got charged. Now the next question comes, what is the time it will take to get capacitor fully charged? Will it get charged instantaneously? Means 10 o'clock I'll switch on. So within that fraction of seconds, the capacitor will get charged. The answer is no. So what is this R? So why you are bringing this R? R is the resistance of the connecting wires. Better. Here to explain you, I brought the R. Practically what is R? R will be resistance of connecting wires. And what is the capacitance? Capacitance is not something intentionally brought in the circuit. It can be unwanted capacitance. Unwanted by whom? Any conductor will have capacitance. I think this is a stage what you have reached here. Don't think that only if you bring capacitance circuit, there'll be capacitance. Unwanted capacitance will be there. What is unwanted capacitance? Because what we concluded, any conductor will have capacitance. That's why you got some numericals in the exam also. There's a conductor, then there's a sphere they brought, then they asked the capacitance of this also. Can you remember? It's a very good numerical. So don't think that capacitor means only parallel plates, spherical or concentric shells. Any arbitrary shaped conductor will have capacitance. So definitely when you go for electrical, electronic equipment, we use metals, we use conductors to construct various shaped objects there for the working of that equipment. So all the different elements will have capacitance. All the different elements will have resistance. All the different elements will have inductance also. So whenever any electrical, electronic equipment, so initially how do it will behave? So we should find out the effective capacitance of that equipment and effective resistance of that, effective inductance. Then how all these three elements are. So then I'll bring a circuit. Then because why, what is this cell? Because whenever you start using any electrical, electronic equipment, you are going to energize it. No, take example fan. You want to operate the fan. You should energize it. The cell is what? The energy supplied to the equipment here. And what is our unwanted resistance? What is C? Unwanted capacitance. This is the thing. That's why in the book, see, if you refer some Resnick and all, it just said transient current. What all? Transient behavior. Better you say transient. What do you mean by transient? Unwanted transient behavior. And next we say steady behavior. Which is wanted here? The steady behavior is what needed. You take mobile, laptop, television, everything, the steady behavior is what needed. So all the equipment, I should use it. So and the transient is what? Unwanted one. So when you switch on and off, so when you switch on the equipment, initially it will have transient, afterwards steady state will come. Or when you switch off, the moment you switch off, transient behavior will come. Then after some time, steady behavior. So this is unwanted. This is unwanted. Finish all. Unwanted means it should be as minimum as possible, no? And it should exist for as minimum as possible. So what I should do to minimize this transient behavior is what I'm going to introduce here. There's actually background. I'm making clear. Of course, if you look at our books, they bring capacitance, two capacitors, series, parallel, all. It's like a funny thing what we have introduced. Practically what happened, the whole capacitance I should bring C here, the whole resistance I should bring it here. Later on what happened, for numerical purpose we have brought it. So transient word comes, so you should not get get disturbed here. So it's just like a unwanted behavior. The initial RC circuit behavior is what the transient will call it. Okay, let's go for, I'll switch on the circuit. Then a current will flow through the circuit. Let it be I. Again from KVL, plus minus, and here a charge will get induced, and further the charge will flow. The rate of flow of charge is what? The current. The rate of flow of charge will be the current here. Then applying KVL. Even capacitor, it's the same conventions what we had earlier had, we are going to follow it. Any general passage, they can ask you the transient behavior, the steady behavior, equipment. So the generalized idea also is needed, just not only numericals. So applying KVL plus C minus VR, or directly I write it since you are aware of K loop equation. The drop across resistor is what? VR, no? The drop across capacitor is what? VC. All set equals 0. Look at what is I. Now, who is responsible for the charge across capacitor? This current only. So here the charge across capacitor is increases. So therefore, this I is equal to plus dq by dt. If charge across capacitor increases, I should be equal to dq by dt. Or we can call this a charging current. If charge across capacitor decreases, then the current through the capacitor should be minus dq by dt. There's a convention. There's a convention. Now let me write here. What is I? This is dq by dt r q by c 0. So this will be E minus q by c equal to dq by dt into r. Let me adjust in some form. Let me integrate this. So this will become dt by rc. Initial charge across capacitor is 0. We'll assume initial charge across capacitor is 0. So at t equals 0, what is the charge across cap? 0. At any instant of time, let the q be the charge. So this will become minus log of EC minus q t by RC, where this lambda, RC I'll call it lambda, this called as a time constant of circuit. I'll give some name. Anybody, what can be unit for this? What are the unit for resistance? I'll show it here. Resistance, what I can write it as V by I. Charge, the capacitance, I can write it as Q by V. And further, this current as Q by T. So what is the finally we got lambda. Lambda is some sort of seconds, no? So what is the unit of that lambda? Time constant. So therefore it's called as time constant of the circuit. And it depends on what? R and C value. Further, this will be putting the limits minus of log of this, sorry, this negative sign, I'll send it to RHS. So this will become log of so this should be equal to log, I'll send on this side. So 1 minus q by CE should be equal to e to power of minus t by lambda. So expression for q will be CE so look at the charge, how it varies. It varies exponentially. Then if I differentiate this, what do I get? I'll get current. So dq by, or I'll write expression for potential across capacitor. This should be equal to q by c. So what is the drop across capacitor? So it will not increase suddenly, it will not increase linearly. The charge across capacitor will increase exponentially. So sudden charging of capacitor, not possible. Sudden removing charge of capacitor, not possible. A good example, bucket, say that's why. So when we say bucket, suddenly can you take out water from bucket? Prodded or pen, you should turn that on. Even then water should come out. No? Instantly what happened? The water cannot drain out. Instantly you can't add water to bucket. Gradually you have to add. If I provide a small hole to the bucket, only through that if you feed water, suddenly you cannot fill up, suddenly you cannot drain out. It's over. The same thing with capacitor also. Suddenly you cannot charge, suddenly you cannot discharge. So gradually it should be charged. So how do that charge will vary with the time? Exponentially increasing. Let's go for current. I'll differentiate this equation. I is equal to dq Ce minus of this will be 1 by lambda e to power of minus t lambda dt. So we know I equal to dq by dt Ce by lambda e to power of e to power of minus t by lambda. What is lambda? R by c. Look at the current. This I'll call it as charging current, because this current is what responsible for increasing the charge across capacitor. We'll call this as charging current. So how do it will also vary exponentially. So put t equal to 0, initially E by R, after a long time will become 0. So how the charge, all the quantities, they vary. Almost I think every problem you do come across the equations of this kind only. So when I plot the graphs, let me compare all the graphs here. So first we'll go for charge 1. This is Ce, this is charge. So the charge across capacitor, it will increase exponentially. Already I have come across exponential graphs. So this is time. The x-axis, I'm taking time. The y-axis is charge. Charge in coulombs. So you put it this one. So in terms of lambda, I'll express here. Lambda, 2 lambda, 3 lambda. So this next again, after this. Okay, we'll do one thing. So this was the expression for charge, no? Q equal to Ce. You do one thing, take calculator, put t equal to 1 lambda, 2 lambda, 3 lambda. You know exponential 1 minus 1 by e, 1 by 1 minus 1 by e square, 1 by e cube. Correspondingly, you'll get the value of q in terms of Ce. So first for at t equal to 1 lambda, what is the expression for charge will be? Ce 1 minus 1 by e, no? E 2.7, 1 by 2.7, you'll get certain value. So how much it will become? It will become 63% of the final value. 1 minus 1 by e, 0.63 it will come. So this will be 0.63. And this time constant is what I brought it like this. And this is 0.63 Ce. So how to define time constant of circuit? Time taken by the RC circuit for the charge across capacitor to become 63% of final charge. It's called as 1 lambda. This is something very important. So this everything is called like a transient behavior. I'll write it. Transient state. After this is what is called like a steady state. Afterwards, almost the charge remains constant. This everything. In steady state, you look at the charge almost constant. You do one thing, put T code 2 lambda, 3 lambda. After 5 lambda, the charge will become almost 99% of CE or 0.99 times of CE. So further you make it 6 lambda, 7 lambda, 8 lambda, 10 lambda, 100 lambda. Almost the value of Q will be approximately equal to C. So therefore almost I'm drawing a constant curve, almost a straight line. So when you switch on any circuit, RC circuit, the charge will not immediately will become C. It takes time. So that is what the transient state what we have here. How much of time? So usually 5 lambda practically, theoretically it will become infinite. Are you able to analyze this? So when the charge will become equal to C, if you look at this equation, put T equal to infinity here, then Q will become C, This is called like a steady state charge. So for our convenient purpose, I'll write it as Q infinity. So what is Q infinity? It's called as steady state charge here. After long, the charge that exists in capacitor at steady state means theoretically what will happen when it will be C T equal to infinity. Practically what happen after 5 lambda. So lambda is what, like, sir, I'll choose R and C value equal to such that 1 second. Then what is 5 lambda? 5 second. After 5 second, almost the charge in capacitor will be equal to C. Practically. So 5 lambda is what we have made a convention. After 5 lambda, the circuit will attain steady state. Okay, now what is use of this? You can ask question. Okay, sir, fine. I'll switch on circuit. This is unwanted, no? So let's take the television. I'll switch on. After 5 minutes, what happen? I will get the full clarity of the screen, the brightness, everything. How will you like it? Will you purchase that particular TV set? Means you switch on the television. After 5 minutes, what will happen? The display will come into picture. What are the brightness are there? Slowly the brightness will increase, and so what you did all the settings, no, that will get reflected after 5 seconds. Also like a 5 minute, let lambda equal to, you designed a television set. You are very good. I designed it. The time constant is 1 minute. The resistance capacitance of the LED TV is such that the time constant of circuit is how much? 1 minute. Then when I switch on that LED TV, after 5 minutes, what happen? It will show the normal response. Normal response means what you are seeing now. So 5 minutes will you wait? It's a stupid, no? Better to put in dustbin. So what is this? Do you want delay of the response? No, you want immediately, no? What all that action that television should perform, the picture, the sound, everything, no, it should display immediately with full clarity. Or you want to change the channel. After 5 minutes, the channel will get changed. So it's a long process, no? So therefore, for electronic and electrical equipments, so what should be the time constant? Should be as least as possible. It's good. To make it zero time constant, what is needed? R and C should be needed. So can you construct any electrical electronic equipment with resistance 0? Means no conductance should be there, not possible. So they will have. So therefore the design of the equipment should be such that it should be 5 lambda. This you can see more in the laptop now when you switch on. Some laptops will take 2 minutes time for the operating system to come and work. Okay, got this? Some laptops will immediately within 10 seconds open, they'll come into the picture and they'll start working. So what is the problem? The lambda here. So the designing of the laptop matters here. In that open, the R, C, L, all the matters. So transient state is unwanted state. So I had to write it clearly here. So this unwanted, this should be as least as possible. This state should be as least as possible. No engineer will predict, and any equipment get damaged, no, will get damaged in the transient state only, because we never design any equipment to work in transient state. The equipment is designed for steady state. But look at the year. we design we design equipment so where the things are constant. It's like that one. But here what happened? Variable things are there, so definitely what happened? The behavior will be different here. So any equipment get damaged, no, either when you switch on or off. 99% of the equipments will get damaged during this particular. The reason is this unwanted state on, because the engineer will not design the equipment for this particular state. He has designed this, but this unwanted state will come into existence. So therefore, at the most, what he can do, he can just minimize it. Because see, the operation where the equipment will get operated here, the equipment will not get operated here. So this unwanted thing, it has come suddenly. But sir, we know that yes, even if you know, you should design for this state only, no, not for this. So therefore, the equipment will get damaged here only. This is a very, I'm telling this one, once you become engineer, no, then what all you, this transient state, no, you pray to it that please don't disturb my project. Like errors in the error analysis, the error, the way it propagates, no random error. Here also the transient state for all electrical electronic equipment, there's a big headache. There's a any good, you can say, theoretical question they ask you. So there's a background. That's why I gave this one. Okay, let's come for the, there's about the charge, current, everything. So let's look at the mathematics here. How the circuit will behave at various instants of time. So this was the circuit what we had. Let me draw once, then I'll, there's the main circuit what we had. No, I'll switch on the cell. At t equals 0, how the circuit will behave. At t equals 0, what is the expression for current? Put t equals 0, e to power of 0, 1. What is the current? E by R. So therefore, the capacitor will behave like a short circuit. Though capacitor is there, it will behave like a short circuit. So where capacitor gone? It will behave like a short circuit, just like a wire. Means it will have infinite capacitance. So still I'll write C only there. So wire means what? It will have infinite capacitance here. And what is the current that will flow through this? This is t equal to 0. In place of capacitor, what you should write? Short circuit. Why, sir, you are replacing short circuit? At t equals 0, what is the expression for current? We have an expression for current is like this. No? Look at this equation. No? Put t equals 0, e to power of 0, 1, e by R. So current will be e by R. So there should be one resistor in cell only. So in place of capacitor, what I should do? Short circuit, I'll place it. Then at t equal to infinity, put t equal to infinity, e to power of, so I will be 0. So at t equal to infinity means at steady state. So in place of capacitor, I should put open circuit. So why you are bringing open circuit here? Because no current through the circuit. So what should be the I infinity? Should be 0. Okay, got this one. So for what is I infinity, why it is? E by R. This is the reason. So in place of capacitor, what you should bring? Open circuit you have to bring. Means like, okay, this is unwanted capacitor. Means the unwanted capacitance of circuit will behave like a short circuit. Here will be open circuit means what? Short circuit means infinite capacitance. Open circuit means no capacitance here. No capacitance. So this what the unwanted capacitance resistance will behave that one. So there's a very dangerous one. We can only minimize it. We can't eliminate. I can't make R and C 0. Along with this, a wanted capacitors will be there, a wanted resistance will be there. There's the other part. So what are the types of problems? You're going to get two types of problems. What at any instant of time, at t equal to 0, at steady state. What will happen to the resistance VR? So here just put t equal to 0, all that one. Look at the voltage across capacitor. Put t equal to 0, VC will be 0. After long time, the voltage across capacitor, how much will be equal to? Equal to applied EMF. So I think you know enough of open circuit condition. No? What is the drop across capacitor? No, equal to applied EMF only. What is the energy stored in the capacitor? That energy stored in the capacitor is needed. U infinity should be equal to the drop across capacitor. How to find out the drop? How to find out the drop here? I think VAB should be equal to C into VAB square by 2. And according to the KVL, what is VAB should be equal to? Should be equal to E. Can you remember writing loop equation? I'll write it U infinity. So this should be equal to C E square by 2. This is the energy stored in the capacitor steady state. There will be energy. And what is the steady state? In terms of steady state charge, you can write it as Q infinity square by 2C. So what is the charge across capacitor? No, Q infinity should be equal to C into VAB. Or this is C. I think that's what I wrote earlier in the graph. No. So what is this? Steady state charge. Okay, this is about the initial theoretical ideas, the graph, that one. So similarly, we'll plot graphs for what is that lambda? The definition of lambda, something very important. So how to define lambda? Time constant of circuit. Time taken for the charge in a capacitor to become 63% of final value is defined as time constant of the circuit. So time constant lambda, what is the definition of it? Time taken by the charge in capacitor to become 63% of final value. What is the expression for how the current will vary? Let's plot the variation of current. At t equals 0, current will flow. That is what I naught we say. No? And it will decrease exponentially. Exponentially decreasing, and this is t is in seconds. So here what is 1 lambda? The 1 lambda we define it as what is the 1 lambda? Put t equal to 1 lambda, it will become 37%. So how much of current here will be known? The value will be 0.37 I naught. So what is another definition for this? Time taken by the current in capacitor to become 37% of initial value. What is initial value? Initially, how much of current will flow? E by R. Finally, how much of current will be? 0. By the current in capacitor to become 37% of initial value. So like this, we define the time constant. Either you can define for any of the curve in terms of charge or current. The definition slightly changes. Put t equal to 1 lambda, then calculate the value of I in terms of E by R. We'll end up with this much here, 0.37 E by R. Now, if I vary, if I increase R, how the response of the graph will be. Let's compare the two circuits. Is exponentially only, curve little bit appears somewhere straight. So finally what happened, there's an expression for the charge. Now can you say anything about the capacitance and the resistance of the circuit? Finally, both the curves, I'll redraw it some because it will give different meaning, different shapes, different meanings are there. This is dotted final, this is. And finally, both will be parallel. Anything can you say about the two circuits? Two circuits, their response are plotted. The same cell will, the same EMF. EMF is same for both. Can you say anything about the capacitance and the resistance? So here, look at the final, the same, like a two circuits, two RC circuits, two circuits are energized by the same cell of EMF E. Look at the final steady state charge. Both are having same steady state charge, no? And the steady state charge, it depends on what? The steady state charge depends on what? Capacitance and applied EMF. So definitely here, there's a cell, there's a first cell, there's a first circuit, second circuit. Same cell will energize it. So I'm just asking you, can you say anything about these values? So what do you say capacitance? Must be same, no? Any reason for the steady state charge is same? So both will have same capacitance, C1 equal to C2. This is the conclusion. What about the resistance? This I'll call the first one. Let this be second one. Can you say anything about the capacitance C1 equal to C2? From where? Looking at the steady state, this one. Okay, now after this, come for the resistance. Anything can you say about the resistance? You should take help of time constant. See, that's all. The basic idea stays there. So, what is the time constant? Time taken for the charge across capacitor to become 63% of the final value. So, 63% somewhere the curve will come here. The curve will bring it here. Let it cut it like this. Now, from here you drop this. Two different things are there, no? Yeah. Now, look at now with this. Can you say anything about? So, which will have more time constant? This will be lambda 1. This will be lambda 2. No? Anything can you say about lambda 2? Is greater than lambda 1. And what is lambda? Time constant. So there should be R2 C2 should be greater than R1 C1. Since C1 equal to C2, so therefore R2 greater than R1. You have to analyze from here. I'm making clear. Already they have asked in advance, can be asked anything further. So you just do remember the idea of time constant. The shape of the curve, it matters. Suppose if steady state charges are different, no, then little bit difficult to interpret.